Let's work through part B, highlighted in red here. We have ammonia now, that's NH3, reacting with HNO3, which is a strong acid. Now I could call my ammonia, which is a base, just B, but this isn't a very complicated thing to write. So there's my base, okay? It is reacting with the strong acid. And remember, I suggest you use this as your strong acid because the NO3 is a spectator. That way it's really easy to see the proton swap that occurs. The base is the proton acceptor. When it accepts a proton, it becomes NH4+. When the water donates, the H3O plus donates because it's the acid, you end up with water. And that is a one-way reaction because the strong acid pushes it to completion. Now when we have this one-way reaction, we have to do an ICF table where we put moles into the table. This is how we do a limiting reactant problem. So we need the molarity of each thing. Now if I read across where it's red, I have the molarity and the volume of the base. So to get the moles of the NH3, this guy, I'm going to take the molarity that they gave me, 0.350, and that's moles per liter. And I'm going to multiply by how many liters I have, 0.188 liters. That's going to give me with the moles of this base, and it is 0.0658 moles. And I can plug this in. Okay? So now I know how many moles of the base I have. They give me about the acid the molarity, but they don't give me the volume. So I can't do this to get the moles, but they tell me it's at the equivalence point. At the equivalence point means this number, by definition, has to be the same number as what we had for the base. Before the reaction takes place, this would be 0. I consume the smaller. Well, they're both the same size, so I consume a negative 0.0658 on the reactant side, and I produce 0.0658 on the product side. That consumes all of my weak base, all of my strong acid, and produces this weak acid. Okay, that's a weak acid. That's what's being produced. That tells me right now that the pH of this thing needs to be below 7 because that's an acid. All right, so now when we're at the equivalence point, we always have to reestablish the equilibrium in order to get the pH. There's nothing here to calculate a pH from, but this guy is an acid, and as such will act as an acid. Oops, I don't want to write the amount. What I want to write is the substance. As an acid, it will behave so with the water it is surrounded by. Now I have a lot of students who struggle with writing this reaction, and they're trying to memorize and see patterns. This is an acid. If you can recognize that as an acid, what does an acid do? It donates a proton. So let's have it donate to the water. Once it donates, it's not got it anymore, so it becomes NH3. It took an H plus off of here and stuck it onto here, so that becomes H3O plus. These are aqueous. Okay? It's an equilibrium, so we don't want an ICF table, but an ICE table. And what do we put into an ICE table? We put molarity, capital M, all right, molarity into that table. Do we know the molarity? No, right now we know the moles. What do you need to know in order to get molarity? Well, the molarity of that ammonia, ammonium ion, NH4+, is going to be the moles, which we do know, 0.0658, divided by the volume that we don't know completely. What do we know? If we look at our table here, our information here, it tells me I had 0.188 liters of the base. So I knew part of the volume, 0.188 liters. That's of the ammonia. I have to add to that the liters of the HNO3. The way I'm going to get the liters of the HNO3 is I know the moles of the HNO3 and I know the molarity of the HNO3. From those two things I can get the volume. So I'll do that down below. The moles was 0.0658. That's how many moles of HNO3, or the nitric acid, I put in. Of the nitric acid, I know the molarity, and that was 0.447. And that is how I'm going to get moles. Moles are canceling. That's how I'm going to get the volume in order to put it here to get the total volume. When I divide those two numbers, what I end up with is 0.147. 0.147. It's almost the same volume because they're closer. Boy, do I like that number. One is 3 times bigger. I would expect it to be a third the size. I'll double check that. We'll work it as if this is correct, okay? So we'll keep on working from that volume right there. I'm going to double check what I have sitting over here. 0.147, that's what I put over here. All right, so now I've got my moles divided by the total volume, and that's going to give me the molarity of 0.196. Where does that go? That is the molarity of this guy, 0.196. This whole subroutine was used to get that value from that value. That's kind of a hassle. It's a lot easier when their molarities are the same, because when their molarities are the same, you know their volumes are the same. Now, I don't care about the water. I know before this equilibrium is established that these are zeros. So now I'm going to consume a little bit of it and produce a little bit of it, produce a little bit of it, and leave me 0.196 minus x, x, and x. Well, how do I solve for x? Well, I know that this is an acid. Ka is equal to the ammonia concentration. I'm writing the law of mass action here. H3O plus concentration divided by the ammonium concentration. So that is the expression that comes right out of this. Then I start plugging information in here so I can solve for my x. What is Ka? Well, Ka, they didn't give to me, but they did give me Kb. So I take Kw divided by Kb of 1.8 times 10 to the minus 5. And that is going to give me the Kb. It is 5.56 times 10 to the minus 10. And that is going to be equal to x times x, or x squared, divided by, what we see here, 0.196 minus x. Tiny k. Tiny k, good assumption, I'm guessing. I assume that it's so much smaller than this I can ignore it. And then when I solve for x, it will be 5.56 times 10 to the minus 10 times, I'm bringing the 0.0196 over and up. That's equal to x squared. But what I want is x, so I take the square root of both sides. That's going to give me an x value equal to 1.04 times 10 to the minus 5. Check my assumption. Is x much, much smaller than that number? Yes, it is. So that's a good assumption. Check what I'm trying to solve for. pH. X is the H3O plus concentration. So if I take the negative log of 1.04 times 10 to the minus 5, I will have my pH, right? That's what I'm trying to obtain, is the pH of this solution. That's going to give me a pH equal to 4.98. And as we said, we would expect this pH to be less than 7 because we have a weak acid being formed in this solution. Indeed, it is less than 7, so I like my answer.